Hello, this is a podcast on nuclear chemistry. In the first slide, I go over the difference between a chemical and a nuclear change. So, in your notes, you should have these filled in. Um, a chemical change involves changes in bonding between atoms. So, between atoms, we have chemical bonds, and these bonds may be broken and rearranged. And when you do that, you trigger a chemical change, something new forms. And this can only occur with electrons, so it happens outside of the nucleus of an atom, and the nucleus remains unchanged. So this is what a chemical change is. This is what we're used to. However, now we're learning about nuclear changes, and nuclear changes occur in the nucleus of the atom. Remember that the nucleus has protons and neutrons, which have a mass. Um, and electrons are found on the outside of the nucleus and they don't have a mass. You have to remember what an isotope is. An isotope, for example, here, um, an isotope is composed of different masses, but it's the same atom. So, for example, carbon has a mass of 12 here, but this other carbon has a mass of 14. So they're the same element. It's just that they have different masses because they have different number of neutrons. So neutrons goes here. Um, Here is uranium. This particular isotope has 235 mass units. And this particular isotope has 238 mass units. So that implies that this uranium has more neutrons than this one. Okay, remember these two are still uranium, therefore they have the same number of protons. And then these two are still carbon, so they have the same number of protons. The only difference is the number of neutrons. So remember nuclear symbols from semester 2. You write the symbol, this is uranium. You write the mass on top, and you write the atomic number at the bottom. So just remember how to write these because we're going to be using these a lot. Here are some more examples. Carbon 12, that's the mass, but it could also be carbon 14. And then at the bottom we put the proton number. The same thing goes with americium, and that one um, has the same number of protons because it's the same element, but different number of neutrons, therefore they have different masses. So that is americium. Here's another one. This is very important for what we're going to learn. These are called subatomic particles: protons, electrons, neutrons. Protons, remember, they have a mass of 1. Electrons don't have a mass. Neutrons have a mass of 1. Protons, here at the bottom, we write the charges. So instead of atomic number, because can't really do that, because we're talking about subatomic particles, we put the charges of the subatomic particles instead. So the proton has a +1 charge, electron has a -1 charge, and the neutron has a no charge, so it's neutral. So just keep that in mind. Now here's where we start really. This is where we really start the lecture. So radioactivity just means when an atom is so unstable, it's so heavy, its nucleus is composed of way too many protons and neutrons to a point where it becomes unstable. And when an atom becomes unstable, it starts to get rid of particles, and these particles are released from the nucleus. Sometimes energy is released as well. Sometimes only energy is released. Sometimes only particles. Sometimes it's both. There are 4 different types that we're going to learn, and we're going to know how to predict the products. So if something undergoes alpha decay, we'll know exactly what forms. Sometimes an atom will undergo beta decay, and sometimes it'll go positron decay or electron capture, and that all depends on nature. So here is the first example: alpha decay. So alpha decay is one way unstable atoms can use to become more stable. During alpha decay, an atom's nucleus emits 2 protons and 2 neutrons. And we can see that here in this equation, this example that I gave you, you should write it down in your notes in the box where it says example. So you're going to write uranium, you're going to write the mass, and you're going to write the atomic number. And this uranium's undergoing alpha decay. So we draw an arrow, and it's releasing 2 protons, so we put a 2 there, and 2 neutrons. And both protons and neutrons have a mass, so 2 plus 2 is 4. So that's why we have a 4 here. And if you look at the periodic table, the identity of something that has 2 protons is helium. So this helium, this helium is what is produced or emitted. And again, we have to balance this out. So if you got rid of 2 protons, then you have to subtract that from here. So 92 minus 2 is 90. 4 minus 238 is 234. Again, you're releasing this helium from this. So you have to subtract this because it's going away from this original nucleus. And when you do the subtraction, you get this. And if you look at the periodic table, the atomic number, so everybody go to the periodic table and look for 90, and it'll give you the new identity of your atom, which is thorium. So you went from uranium, it was so unstable, it released helium, and then you ended up with thorium. And beta decay, again, it's another way an unstable atom can become more stable, and something strange happens in beta decay. And that is that the proton, one of the neutrons ends up transforming itself into a proton and an electron. And the proton ends up staying behind while the electron is emitted. And if you look at the nuclear equation here, we have cobalt right here. Atomic mass of 60, atomic number 27. It undergoes beta decay because it emits something called a beta particle. So the beta particle, again, has no mass, and it has a -1 charge. And remember, during beta decay, you have to add another proton because the neutron ended up converting itself into a proton. So we add 1 here. So instead of 27, it's going to be 28. And if we change the proton number, we change the identity of the atom. So it's no longer cobalt, it's now nickel. The mass stays the same. And if you think about it, a neutron has an atomic mass unit of 1. And if it turns itself into a proton, which also has an atomic mass unit of 1, then there's no net gain in mass, because you have something that weighs 1 and then it converts itself into something that also has a mass of 1. So the mass is unchanged. The only thing that changes is that you gain a proton, so you change the identity, and then you lose an electron. Go ahead and use the example and see if you could figure these out. Then go ahead and press the play button to see what I did. Okay, so samarium has SM as its symbol, has a mass of 146, and it has an atomic number of 62. It is going to undergo beta decay, so that means it's going to release an electron that weighs 0, has a -1 charge. Okay, so you could write it as like that, or you could also replace it with this symbol right here, a beta symbol. And it's going to, again, a neutron gets converted into a proton, so it has a new mass of 63. Notice how 63 minus 1 is 62, so you could think of it that way too. And the mass doesn't change. If you look at the periodic table, 63 is for europium. Lanthanum has a mass of 140, and its atomic number is 57. It undergoes beta decay, so you have a beta particle being released, and you're gaining a proton, so 58. 58 minus 1 is 57, so it balances out. Mass stays the same. New element that forms, so look for 58 on the atomic number side of the periodic table, and that is cerium, so Ce, cerium. Okay, and that's how you do beta decay. All right, easy peasy. Next one, third one, positron decay. I think this one is probably, it's very similar to beta decay. If you look here, positron has the word positive in it. It's really weird. Um, it's basically a positive electron that is being emitted. So here it says positron decay is another way to become stable. This occurs when a proton transforms itself into a neutron and a positive electron, which is really weird. This positive electron is a positron. Okay, like electron, but positron, positive. So this positron is emitted while the neutron that also forms stays in the nucleus. It's like beta decay, but instead of a negative one here, it's a positive one. So if you write this example down, the mass doesn't change, but you have a one charge here. And again, you want to balance it out. So 1 plus 29 makes 30, and 29 becomes copper. So this is what positron decay looks like. It just means you're producing a positively charged electron and you're reducing its proton number, since that's what you're getting rid of. You're getting rid of a proton. So therefore you have to subtract one. Okay, so let's go ahead and try these examples. Go ahead and try these on your own and then check in with me. Again, it's like beta decay, but instead you're getting rid of a proton and you have a positron. So go ahead and try it. Look at your notes if you need help. 146, right? That is the atomic mass. Samarium has, let's see, an atomic number of 62. You are going to form a positron, which looks like this. Positron, and then you're gonna have 61. You're losing a proton, so instead of 62, it's 61. And if you look at the periodic table, 61 is PM. Okay, so PM. All right, go ahead and try the next one and press play. So lanthium, La. Lanthium has a mass of 140 here. 57 is its atomic number. It's undergoing positron decay, so you have a positively charged particle, which weighs nothing. And you're going to have one less proton, so 56, and the same mass. According to the definition, you have lost a proton and you have a new particle that weighs less, and 56 would be barium. Okay, so it will be barium. Electron capture. It's in the name. Basically, what happens is that one of the electrons from the outside of the nucleus, it gets injected into the nucleus. It just literally just crashes into the nucleus. So during this process, during electron capture, you take in an electron And because the electron is in the nucleus, um, you could think of it as this electron is neutralizing one of the protons. And so you're basically getting rid of one of the protons. So in this case, um, you have zinc, and zinc gains an electron. So it's going to neutralize one of these protons. So it's going to become 29. It's going to have an atomic number of 29, and therefore you change that identity. And because this electron weighs nothing, the mass doesn't change at all. Okay, so let's go ahead and try that one. Samarium, so we're gonna write SM. It has a mass of 146. Samarium has an atomic number of 62. It undergoes electron capture, so it's gonna capture an electron, right? And because it's going to neutralize a proton, we're going to get rid of one. 61, 146. And if you look at the periodic table, the new element that forms is going to be PM. Okay, PM. Okay, so that is electron capture for that one. Now go ahead and try the next one. 140. And has an atomic number of 57. It's going to capture an electron, neutralizes one of the protons, and its new element is going to be barium. Barium. During gamma radiation, what happens is a big wave, a huge wave, is released from the nucleus, and this wave is very dangerous. It could cause DNA damage. It could cause cancer. So gamma radiation is one of the most dangerous types of radiation that exists. Um, Go ahead and try them out. And once you're done, check your answers. And this is a mixed practice, so try to memorize, make flashcards, try to memorize these, and then try these problems out, okay? And hopefully you will understand it. Just one more thing to know, transmuting here means it's transforming. So it's going from BK247 to something lighter, like AM243. So notice how the mass, it goes down by 4. So therefore, you can infer that you're probably getting rid of a helium. So again, when you're doing these, make sure they balance out. 27, 1 plus 26 is 27, 27 minus 1 is 26, 26, 84 on the left, 84 on the right, 97 on the left, 97 on the right, 63 on the left, 63 on the right. So that's how you could tell if you're doing it right or wrong. Remember that identities should be changing because you're forming lighter elements. So in reality, uranium, it's very big. Um, it's a very big atom. It's not just going to undergo one type of decay. It's going to go through a series, sometimes even 10 or more. And so in this example, uranium undergoes alpha decay, then it undergoes beta decay, and then it undergoes beta decay again, and then it undergoes alpha decay. So, we could still apply what we learned to figure out what our final product will be. So for example, uranium is undergoing decay, alpha. It's going through alpha twice, so that means it's emitting helium twice, right? So we can put a 2 in the front like that. So that means it's emitting some particle that has +4 charge, right? 2 times 2 is 4. So it's emitting a particle that has 2 particles that have a total of +4 charge. And Then it undergoes beta twice. Beta, remember, is electron, right? And it undergoes that twice. So we have a nuclear, we have a charge, subatomic charge of -2. And when you add them up, you have a net charge of +2 on the right side. So what ends up happening is that you have a net charge of +2 on the right. So you're gonna subtract 2 from here. So you're gonna have 90, right? Because 90 plus 2 is 92. Now it matches here. And then you have 8 mass units there, right? So, and then 2 times 0 is 0. So when you subtract 8 from that, you get 227. And if you look at the periodic table, 90 corresponds to thorium. So thorium is what forms when you undergo this series right here. Okay, hopefully that makes sense. If not, just rewind it, try to understand what's happening, and you should be okay. You should be able to now do problem set number 1. Make sure you try, check your answers. Make sure that you make corrections and that you upload onto Google Classroom your a picture of your work.